Okay, welcome everyone to my continuation of what is linear algebra. Today I want to explain something very important. What are linear equations, or rather what is a system of linear equations? As we will see, it's all about intersections, and this is a very classical problem. So there's, well, you can ask how certain things intersect in whatever free space or whatever, and that's exactly the idea behind linear equations. People have studied these for hundreds of years. The more modern viewpoint of why should you know what the system of linear equations is, well, in science we like to study toy models, right? So you start by simplifying things. You know that is not the real world or whatever. You start by simplifying things, and if you can't say something about the toy model where everything is much easier than in general, maybe there's not too much hope to go beyond. So, in other words, so regarding to our today's discussion, um, yeah, so life usually doesn't give you linear equations. Most of the time, life is really crazy and gives you some really crazy equations. But if you can't solve linear equations, how much hope can you have to solve anything in real life? So let's just start with linear equations. Kind of the easiest thing you can imagine, the first thing you should try. So let's go. You all know what a linear equation is, right? It's something like this. Let's say I have three variables, and the number of variables is the dimension of the space I'm living in. Okay, so three variables x, y, z. That means I'm secretly, let's say I again work with real numbers, so secretly I'm living in R3. And a linear equation is just some linear combination of those elements. 1 times x, 2 times y, 3 times z equals something. Let's say it equals 0. Um, and what is it? Well, a linear equation is a linear space. That's the whole point. Um, so you have three coordinates and you want them to be equal, okay? Equal to something. In this case, you want them to be equal to 0. And this kind of, well, one of them is certainly dependent of the two others, but you still have kind of two free variables. So in some sense, this should be a plane, right? There should be something two-dimensional. So let's look at this. Indeed, it is. So if you fix x and y to be something like 1, in my example here, um, what it is, well, there will be just one solution. If x equals 1 and y equals 1, then the beta has to be -1 and it's just a point. Okay? If I just fix x, here fix x to be 1, then you still have, well, if you would fix y, we already know you get a point. And now y varies. So for each y, you get exactly one z. And because it's a linear equation, you won't be very surprised if that you actually get a line. So for each fixed x, you get a line. And if you fix nothing, you won't be very surprised that actually you get a plane. Right? So for each, so you can think of now for each x you get a line, and now you vary x, so you get a plane. Right? This is just how it looks like, a linear equation. A linear equation in three variables is a hyperplane in is a plane in R3. So let's say we are working with real numbers, so it's a plane in R3. This is one linear equation. So each linear equation actually describes you a certain linear subspace of whatever space you're working in. Okay? So now let's have a look. What happens if you have two linear equations? Okay, you have two linear equations. Here, 1 and 2, 1 and 2. And well, I've chosen some specific coordinates down here, but let's say it doesn't matter so much. You have sort of a times x, b times y equals c, my first linear equation. Um, what is it? D times x, e times y equals f. So the first thing you should observe is I have variables x and y. So actually, I'm doing things in, let's say, two space, R2. Okay? Actually, I'm working in R2 here. And I have two system of linear equations. So each one of them So let's say I have the green one and I have the red one. Or to be consistent with my pictures, let's say I have a blue one and I have a red one. So one of them, both of them will define a line. Okay, a blue line, depending on whatever A, B, C, D are, they could be like this. And a red line, depending on whatever D and E and F, they could be whatever like this. So what will happen? So generically, so both of them define you a line. So three things could happen. So generically, they would just intersect somewhere, and you had one solution, namely the intersection. If you are, so this case, this is generic case. If you're a little bit unlucky and you have chosen your A, B, C, D, E, F in some, let's say, stupid way, then you might end up with two parallel lines, and then of course get no solution, or you would end up with two parallel lines which completely intersect. So in this case, blue equals red, and then you get infinitely many solutions, or a line of solutions. So everything is a solution, and these are really basically the three cases that happen. So either you have one solution, which is kind of the generic case, which almost always happens, or you have no solution, or you have infinitely many solutions. But keep in mind, the main point is two equations, each one is a line. So just draw those lines, and that's basically what people did, right? Before the invention of more formal like algebra that you write down, like x whatever, you could have studied lines in space. That's what people did for a long time. And formalizing this, you end up with a notion of the system of linear equations. And well, takeaway message from this slide is generically, well, you have a line and a line, so they intersect in one point. If you're unlucky, they don't intersect because they are parallel, which rarely happens. But of course, you can always construct something that they are parallel, or they might even be equal, and then you have infinitely many solutions. Okay. So Gaussian elimination is one of the most crucial things. So if you ever see equations given to you by life, like they won't be linear, they won't be something crazy, and there's almost no way you can ever solve them. And really the miracle that happens for linear equations, which is extremely important, is you can always solve a system of linear equations. And the main point is Gaussian elimination. Okay, and it basically works like this. You have some explicit, so this is a line, so one is some line, two is some other line, whatever, God knows how they look like. And there's some explicit coordinates and you write them. So this is kind of the standard thing people do. There are various ways to write them down. So don't get confused if you've seen others. And basically you write them in some kind of matrix and you remember on which side those numbers actually live. Right? 1, 2, 3, 1, 2, line 3. 4, 5, 6, 4, 5, line 6. And then you perform Gaussian elimination, which is basically a set of rules to transform those matrices. So what you, for instance, can do is you can multiply this first line here by -4, and you get a new first line, right? 1 times -4 is -4, 2 times -4 is -8, and so on. So this is one of the legal operations. You can always multiply a line by something, and that makes sense, right? A row by something, but that makes sense because a row is secretly a line, right? And you multiply the line by something, and if you multiply it by a scalar, it's still a scalar, which is less obvious. But if you think about it in terms of lines, it's also not so bad. You can actually add them together, and you won't change the solution result. So I can, for instance, add my first row onto my second. So first row stays what it is, but I change my second row accordingly. And then I can scale again, for example, and I can add again, whatever. And you end up with an equivalent set of And you do this until you basically have something like this. And this is an equivalent set of equations. And this is now really very easy because you have minus 4x plus 0 times y. So y is gone in the first equation equals 4. And similarly, so minus, this is gone equals 4. This is gone, 8 equals 6. And you can then just easily solve that. Right? Easy. Uh, Gaussian elimination. So this is an algorithm. You just have to do it 5 times, and it's not so hard. The point is, you could always solve linear equations, which is pretty amazing. Um, yeah. Um, so the formal definition is then not much harder. You just have this linear combination, and you always have written in the matrix form, and this is really just equivalent that you want to solve this matrix equation. That's why Gaussian elimination works. So instead of writing a system of linear things like this, so a11 up to a1n, am1 up to amn, you can also write it in this form where the only thing you need to remember that those are the variables here, right? So the x's are the variables. Okay, let me show you some more pictures because it's really just something you need to remember. Um, so remember that in 3 space, that's what I told you. So if you have 3 variables, you live in 3 space, and you get linear equations. So this is 3 variables, x, y, z, and we are living in R3. And you would have 3 equations. A red one, equation 1, a blue one, equation 2, and a greenish one, equation 3. And generically, you just have some planes that do something, and you will see that planes that do something intersect in one point. So you get one solution. You also could end up with, let's say the red is just completely parallel to the blue one, so you can ignore it. You could end up with a line of solutions. Yeah. Or everything is just one thing. So you can end up with a plane of solutions. So here everything is just equal. Or if you're unlucky, then they are just completely different. They're basically parallel to one another, and you end up with no solutions. So generic, it's the same story. I just want to illustrate in higher dimensions, it's the same story. You end up with one solution. This is kind of the generic case. You might end up uh, with infinitely many solutions, or you are really unlucky and you end up with no solution. But almost always this will be the case. Anyway, I hope it was illustrative, and the only really thing you need to learn is Gaussian elimination, and keeping in mind that this is a very classical question you could ask, like, how do linear subspaces intersect? Okay, this is it for today, and I hope to see you next time.